Yeah, good morning. So, in this lecture we are going to talk about random variables. Now, as usual we will have to first learn what is a random variable. Actually, it so happens that suppose you have an experiment, right. So, we have seen in the last class that if we have an experiment, then we can assign, it will have certain outcomes and we can assign probabilities to its various outcomes. We can even define events which are a subset of all the possible outcomes and we can assign probability to them. Now, it is not always necessary that we will have to assign probabilities only to outcomes. Rather, we can start assigning probabilities to functions of outcomes. For example, we can say that suppose you cast a die, and now if you cast a die, then the probability, then what are the outcomes? The outcomes are 1, 2, 3, 4, 5 or 6, and you can say that whatever face comes up, I will give you 10 rupees for each mark. So, if a 4 comes up, I will give you 40 rupees. Now, how many rupees I am giving you now becomes a function of the outcome, is it not? Now once I define this function, now I can start talking about what is the probability of your getting a certain amount of money. So, we need not always directly speak in terms of the outcomes, but in general we should speak in terms of functions of outcomes. So, that is the basis of having a random variable. So, a random variable is nothing but it is a variable which is assigned a value corresponding to every outcome. So, for every outcome you are assigning it a value which is a real number. So, it is basically a mapping from the set of possible outcomes to reals, right. So, now once you so now you have a variable which will get values corresponding to every outcome. Now, once you have that, then we can talk about, then we can make statements about this random variable and then talk about their probabilities. So, we can say that what is the probability that you will get less than 35 rupees. You can say make such things. So, what is the probability that this random variable's value is less than or equal to small x. So, what does it mean? This means that this particular notation, that is within curly brackets, a random variable and then an expression concerning random variables, it means it is the set of outcomes of the experiment experiment that we have, such that x of xi according to this rule, because according to this rule corresponding to every xi belonging to S you will get a number which is x of xi. So, what is, so it is all these xi's such that x of xi is less than or equal to x. So, this denotes a set of events or a set of outcomes. Similarly, obviously we can say which are the set of outcomes that x is greater than x. You can make many such statements. That will be obviously the total set minus x less than or equal to x. So, we can make various such statements. Now, this mapping that we are talking about, this mapping should obey in general certain mild properties. So, the properties are that, first of all statements of this kind should belong to should be an event, that is for all values of x, for all values of small x, the set of events that will correspond to this should be an event. It may be an impossible event, this set may be a null set, or it may be the full set S, or it may be any other set, but it should be a set in general. This is a mild condition, because when you are mapping the set of events onto a real number line, real line, etc., there are as we have noted that there are some peculiar combinations to which you cannot assign a probability and it will not be a valid event. So valid events are only sort of countable unions and intersections of intervals on real line. These are some certain technical mathematical things. So that is why this is needed, and it should so happen, you should assign this function in such a manner that the value of x at infinity and the value of x at minus infinity should have 0 probability. This is the these are the properties that you should obey. These are very mild properties. I mean most of the functions will actually obey them to assign this. Now so this is a random, basically simply speaking, a random variable is a function of the outcomes of an experiment. Okay. So having said that, we can see an example. For example, for the die experiment, the outcomes are f1 to f6, and as I said that let xfi is equal to 10i. So I am saying that I will give you 10 rupees corresponding to every point that comes up on the die. So then what is the probability, what are the set of events such that x is less than or equal to 35? Obviously it is f1, f2 or f3, because for f1 xf1 is 10, for f2 xf2 is 20, and this is 30. So the set of events for which this is satisfied are f1, f2 and f3, correct. If I say what is the set of events that x is equal to 35, it is obviously the null, because there is none of them will give you exactly 35 rupees. So it is also an event of, it is also a valid event. It is the impossible event, but it is a valid event. Similarly, x less than or equal to 5 will also give you the null event, and just to see that property is satisfied, x equal to infinity and x is equal to minus infinity are both 5. So that property is satisfied. So this is a valid random variable. Okay. Now we start talking. So far we have just talked about the set of events. Now we have to, our main interest is a probabilistic characterization of this variable. So now we have to start talking about the probability that capital X is less than or equal to x, because that is our main interest. So now we start talking about once we have defined a variable, we can define what is known as distribution and density functions. So this is a distribution function, density will come later. So what is the distribution function actually characterizes the probability that x is less than or equal to x. This without this, it is the set of outcomes, as we have noted. So whenever you have a set of outcomes, you have a corresponding set of, you can assign a probability to that set of outcomes. Basically this becomes this is like an event, because it is a set of outcomes. All sets of outcomes are events. So now you can talk about the probability of the event. Okay. So only you are talking in terms of x. So the function which characterizes the probability of the events for which capital X is less than or equal to x is called the distribution function of, it is a distribution function of the random variable x, and its value for the value small x is this. Okay. Sometimes we will drop this subscript x whenever it does not cause confusion, but in general you can talk about f subscript capital X of w, which will mean that capital X less than or equal to w. So they need not be same variables, but when we are using same variables, we sometimes will drop this subscript. So for example, our simplest experiment is coin tossing. So for coin tossing, what is the distribution function? So suppose we say, first of all, coin tossing is an experiment, we know what are its outcomes. suppose this outcome is that its outcomes are head and tail. Now suppose I have defined a random variable such that x of head is 1. First of all, we have to define the random variable, that is define the mapping of these outcomes to the real line. So suppose I have defined this mapping that x of head is 1 and x of t is 0. This is my mapping. It will satisfy all probability all properties of a random variable. So now we can again make statements. For example, we can say that x is greater than 1. This is the null set phi. X can never be greater than 1. Similarly, x is less than or equal to a. What is the set? It is h and t. If for all a greater than or equal to 1, because x is always going to be less than or equal to 1, because the only values of x it takes are 1 and 0. So it is always going to be less than or equal to 1. So the set of events are h and t, that is the whole set. So its probability is going to be 1. Similarly, if x is less than or equal to b, when b is less than 1 and greater than or equal to 0, is t. Only for this tail outcome, the random variable, the value of the random variable satisfies this, correct. So the event corresponding to this is the tail event, and if c is less than 0, then this is again phi. So now I can say that what is going to be my distribution function with respect to x. So the moment c goes less than 0, fx is going to be 0, because it is a phi event and the probability of the phi event is 0. For from 0 to 1, it is going to be this t. So if we assume a fair die, that is the probability of head is 0.5 and probability of tail is 0.5, then it will be 0.5. If it is an unfair die, then we can assume any other value, that is suppose the probability of head is p and the probability of tail is 1 minus p, in which case this will become 1 minus p, and then at 1 it will rise. So this is the probability distribution function of this experiment under this of this random variable, right.
So
Yeah.
For the x less than a.
For x less than or equal to a.
So you said for a greater than 1, head and tails.
No.
It will only be heads.
No. X is less than or equal to a, and a is greater than or equal to 1. What does it mean? That basically let a be 1.5. So x is less than or equal to 1.5. This is always satisfied, because x can be either 0 or 1. So the set of events which will satisfy this is h and t. Now suppose x less than or equal to b and b is less than 1, suppose it is 0.9. If you say x less than or equal to 0.9, that is only satisfied by the event t, because x of t is 0. So the probability will be the probability of the tail event, which may be, as you define it, maybe 1 minus p, correct, understood. Okay. So now what are the properties of the distribution function? The properties of the distribution function should be, first of all, that f of plus infinity should be 1. This is natural, because what is f of plus infinity? It is the probability that x is less than or equal to plus infinity. So obviously it is 1, because x is naturally going to be less than or equal to plus infinity. It will, whatever real value it takes, it is going to be less than or equal to plus infinity. Similarly, f of minus infinity will be equal to 0. So this is also natural. This means and should be a non-increasing monotone, rather non-decreasing monotone, not increasing, not non-increasing, non-decreasing monotone. So, which means that if x1 is greater than x2, then fx1 will be greater than or equal to x2, fx2, right? What is it? Why greater than or equal to? Because suppose, because the probability function, especially for discrete variables, we will see what discrete variables are, like the coin tossing experiment. What did you see? That the probability density function rises in steps. So, suppose this is x1 and this is x2, then fx1 is equal to x2 is equal to fx2, and on the other hand, if you have this as x1 and this as x2, then rather the opposite, this is x1 and this is x2, then you have fx1 greater than fx2, and these are the only two cases. So, if you have discrete jumps, then x1 greater than x2 will imply that fx1 is greater than or equal to fx2. So, it either increases or stays at where it is, it does not decrease. That is why it is called a non-decreasing monotone. Monotone means continuously rising, right. So, right. So, this property should be satisfied. Then,
So, but doesn't this depend on what variables we have chosen, what x1 and x2 we have?
no, it does not depend on that.
And their probabilities.
No, it does not depend on that, because as I am moving x on the axis, I am actually increasing the set of outcomes all the time. So, the probability cannot decrease. See, what is the range I am considering? I am considering from minus infinity to suppose x2 here, and x1 is greater than x2. So, first time I am considering this set, second time I am considering this set. So, I am always covering this. So, the set of outcomes corresponding to this are anyway covered in this, and I possibly am including more outcomes. So, the probability will increase. Okay. Now, then it says that probability of x1, if x is less than x1 or less than or equal to x2, what does it mean? Remember that we are having less than x1 and less than or equal to x2. This is to take care of discrete jumps. If the probability distribution function was absolutely continuous, this is a discontinuous function. Okay. It takes a jump exactly at some point. So, x is greater than x1 means that if this is the x1 point, then x greater than x1 and less than or equal to x2 means that it just starts from after x1, okay, and is less than or equal to x2, that will be fx2 minus fx1. Why? Because x1, this interval can be written as the interval that is equivalent to the I should not use this notation. Suppose let us take the interval x1 x2. This can be written as the interval x less than or equal to x2 minus, this is the interval corresponding to this, less than or equal to x1. If you subtract from this interval this, you will get this, and because you have less than or equal to, so the point x1 is actually included in this interval. So, when you subtract from here, the point x1 will be excluded from that interval, therefore, it is less than and not less than or equal to here. So, obviously, the probability of this is going to be, since these are these are disjoint sets. Now these are not disjoint sets, but this the probability, okay. So this is going to be the I mean exactly the probability of, this is a set subtraction. So for set union you have to take, they have to be disjoint, but for set subtraction need not be. So this is simply because this is some outcomes, this is some outcomes. So you have to subtract. So this becomes f of x2 minus f of x1. Yes. Sorry, actually I should write in the center. So so this is how it comes, because this interval I am now breaking up as I am subtracting this from this interval this, and so the probabilities will become fx2 minus fx1, right. Now it turns out that f this distribution function is a right continuous function. That means that the right hand limit will tend to the function, that is suppose for example for the coin tossing experiment, this is the exact point, let us say 1. So this is the coin tossing experiment, this is 0. So here it is 0, we have drawn, and this is 1, this is 0.5, we have just plotted it, this is 1. So just at 1 it takes a jump. So till this comes to the limit, it can be 0.999999 any number of 9s, and still the probability will be 0.5, and the moment it will reach 1 it will go up to 1. So the left hand limit, that is f x, limit of x minus epsilon tending to 0 is not equal to f x, because however small you make this epsilon, the probability of x minus epsilon is going to be 0.5 whatever epsilon you make, as long as epsilon is non-zero. But the moment epsilon becomes exactly 0, that is it becomes fx, it jumps. This is because we are considering discrete jumps and the function is discontinuous. But from the right side, fx plus epsilon, as epsilon tends to 0, will come to the function fx. That is why it is called a right hand continuous function. Okay. So now obviously what is probability that x is equal to x? It is fx minus, because fx minus fx minus is the set x less than or equal to x minus, where x minus is equal to limit of epsilon tending to 0 x minus epsilon, is the set of all points from minus infinity to x, but leaving out the point x. Just that point if you take out, all other points are included. And if you put x here, these are simple limit concepts. So if you put x here, then you are considering minus infinity to x including the point x. So if you subtract this from this, then you are left only with the point x. Okay. So that is why probability that x is equal to x is fx minus, and so on. These are simply derivable properties and they are easy to follow. Now you may have, in general you may have a continuous random variable, a discrete random variable, and a mixed random variable. For example, if you are measuring temperature of this room on several different days, then that variable will be a continuous random variable because it can take any value. If you are measuring, if you are having a coin tossing experiment, then you are having a fully discrete variable. If you are having, now you can in general you can have an experiment where it is a mixed random variable. For example, you can measure, suppose you have 3 different thermometers and each thermometer has some fixed bias, and you are using one thermometer, you are picking up a thermometer and you are coming to measure the temperature of this room. So this picking up of the thermometer will constitute the discrete part of the experiment, because there are only 3 thermometers, there are a discrete set of outcomes, and then you are measuring a temperature. So this thermometer temperature combination, it will again be a random variable that will have mixed properties, right. So you can have, this is an offhand example I have given. So you can in general have, that is, distribution functions may look in different ways. For example, they may look like this, they may look, see, they have to go to distribution functions, they have to start from 0 because f minus infinity is 0, and they have to eventually finish in 1 because f plus infinity is 1 and it is non decreasing. So therefore distribution functions generally look like this. So this is, it will gradually, as you increase x, this will approach 1 and it will necessarily have to start from 0. So this is a continuous function. If we have, as we have seen, if we have like this is a purely discrete one. We can also have a, we can have it like this, that suppose it is, we can have a form which is like there is 3 different continuous segments. So in general distribution functions can be piecewise continuous, that is, there will be a finite number of step jumps corresponding to the discrete part of the experiment, and in between those step jumps there will be continuous variation. So it is general, in general it is a piecewise continuous function with a finite number of step jumps.
Sir, what do you understand by negative values of probability density functions?
Probability density functions
This function
or probability distribution functions. Probability distribution functions cannot be negative.
is right now we have shown if the axis is considered as 0.
No, this is x.
Yes.
This is fx. Fx is always positive. That is the y axis. Okay. Probability distribution functions cannot be negative simply because they are probabilities. So probabilities cannot be negative. That's why. So this is a way of writing that. So any probability distribution function can be written as a, it is, this is called the Layback decomposition theorem. Anyway, let us not get into technicalities. We can understand things very simply, that any such function which is piecewise continuous can be written as a sum of a continuous function and a sum of some discrete jumps. So they can be broken up in, you know. So this part, this continuous part denotes the continuous random variable part of the experiment, I mean the continuous part of the experiment, and this denotes the discrete part of the experiment. So for the continuous part, gx x plus, this is the definition of continuity of any function, that the left hand limit and the right hand limit converge. So gx x plus is equal to gx x is equal to gx x minus. That is why it is called continuous. And for hx, this is there, these are some right hand continuous step functions like the one we have just now seen. Okay. So if gx is 0, then we have a purely discrete random variable. If hx is 0, we have a purely continuous random variable, and in general we have both, right. So, these are the various kinds of random variables that you may have. Now, let us come to probability density functions. Probability density functions are nothing but rates of changes of probability with the value of x. Okay. So how is it defined? It is defined as d of fx by dx. Now, obviously, since the function is now, which means that it is x less than or equal to x, that is the limit. Basically, what I have done is this d of fx of x I am writing in terms of the probability. It is the probability that x lies between small x and small x plus delta x, that divided by the ratio of the interval delta x and limit of delta x tending to 0. So, this is how it is defined in terms of probability. Now, obviously, where this fx will take jumps, this function will become some Dirac delta functions. We know about Dirac delta functions from our network courses. So, obviously, since for all positive increments x, since fx is a non decreasing function, so therefore, this must be greater than or equal to 0 all the time. It cannot go negative because fx is never decreasing. Okay. And how is fx defined? It is minus infinity to x of, that is, if you have the density function, you can derive the distribution function in this manner, simply by integrating. Why from minus infinity? Because from minus infinity you will get a 0 initial condition. Okay, because we know that f of minus infinity is 0. So, you will get just the function fx. The other function which will come for this limit will be 0, right. So, and obviously, now if we put, you know that fx plus infinity is 1. So, minus it. So, this function should be such, it should be such a function that when integrated from minus infinity to plus infinity, it should evaluate to 1, right. And this we have already seen, this property. So, we do not need to see this again. Now, once we have a probability density function, for example, there we always deal with various kinds of probability density functions. For example, we are very common are normal or Gaussian, which has a form like this. Okay, this has, this is a very celebrated distribution function because it has, because of two reasons. Because of a particular property called the law of large numbers, which says that if you have any distribution, any random variable from any distribution, and if you take a large number of samples from it, and if you average them, then that average tends to obey the normal distribution. That's a very useful thing, which is often used for generating Gaussian random variables. We will discuss this. At the end we will have to discuss how in the computer we can generate random variables. Okay, many of you would require it. So, this property, this law of large number property is used to generate Gaussian random variables. Then you have an exponential function, which is typically used in queuing theory. There are various kinds of, for example, there is the uniform function. When you do not know anything about how the probability distribution of a variable is, you can assume that it is uniform. That is, in an interval, within an interval, the probability distribution function is flat. That is the probability of getting any value of x in the interval a to b is the same. They are all equally likely. So, when you don't have any information, it is reasonable to assume that they are equally likely. Okay. And correspondingly, you can have, there are some well known, there are many distributions which are used in various contexts. For example, in reliability context, people use Weibull distribution. In communication context, people use the Rayleigh distribution. So, there are various kinds of distributions. So, I have listed only a few of them. So, this is a binomial distribution, that is in what is the probability that in n fair trials you will get k balls of a white, let us say. So, the probability of if the probability of drawing a white ball is p and the probability of drawing a green ball is 1 minus p, then like that. Okay. So, basically this comes from a simple so these are basically terms of the binomial series, and similarly you can have a Poisson distribution, which are distributions which characterize waiting times between discrete arrivals. So, they are also used in queuing theory. So, this is just an example of various kinds of distributions. Now, we come to what are known as, so we can now talk, previously we had talked about conditional probability. So, now we can talk about conditional probability distributions, we are going in the same way. Okay. So, what is f of x given m? M is an event, that is one. Suppose you know that some distribution f x is given to you. Okay. So, now if an additional information is given to you that capital M has already occurred, that is whatever has occurred satisfies the event capital M, then can you make a more intelligent, can you now estimate what is going to be the probability that capital X is going to be less than or equal to x, already if it is told that the event M has occurred, right. The event M may be related to that same random variable or even otherwise, whatever it is. So, that is again, so this means that the probability that capital X is less than or equal to x given that the event M has occurred. So, that is again by the same rule, it is the probability that this and this jointly both occur divided by the probability of M. This is our standard condition probability rule. This is one event, this is another event. So, probability of A given M is probability of A and M divided by probability of M. Okay. And this has to be a probability distribution. F of x given M is also a probability distribution, just like f x. So, it must obey all its properties. So, obviously f of infinity given M must be 1 and f of minus infinity given M must be 0, and probability of, and you can I mean from this thing you can say that probability of x which is greater than x1 and less than or equal to x2 is again f of x2 given M minus f of x1 given M. That is whatever probabilities x1 and x2 generally satisfy the same properties, this also satisfies. You can also examine, let us say you can also define its density function. Once you have defined the distribution function, the density function is simply its derivative. So, you can define this as d of f x given M by x in the same way. For example, consider the case of a fair die, and suppose it is told that an event phase has occurred, that is the event M, that an event phase has occurred. So, what is M? M is f2, f4 or f6, either 2, 4 or 6 have occurred when M is told. So, and suppose the random variable x is defined as in our previous way, that is for every thing you get 10 rupees for every point on the die. So, now how do you characterize this conditional distribution function? It is 1 for all x greater than or equal to 60, naturally. It is 2/3 for all x between 40 and 60. Why? Because what is the probability that this is what? It is, first of all, find out. So, we have to find out what? We have to find out the probability that x is greater than equal to 40, no, greater than 40, let us say, actually we should write it this way.
So it is less than 60.
It is less than 60. because we have already included greater than or equal to 60 here, right. So it is less than 60, okay, does not matter. So this is for, let us do it on a separate page.
The first condition itself should be less than 60.
No, why greater than or equal to 60?
Then it should be 0.
No, wait, no. So what is this? We want to determine if x less than 60 greater than or equal to 40 given m. This is my problem, okay. So that is equal to probability that x less than 60 greater than or equal to 40 and m given by probability of m. This is my definition. So now what is the probability that x is less than 60 and greater than or equal to 40 given that m is f2, f4 and f6? It is only 4, correct. X is less than 60, what is that is what is the set of event? Probability will evolve later. So this and this, what is the set of event? The set of events is naturally 40, that is basically f4, should not say 40. The set of event is f4 only, because this contains f2, f4, f6, this contains only, this also contains only f4, okay. And what is the probability of m? It is half, because if you assume a fair die then it is half. So it is, because this is f2, f4 and f6. So it is so this one will be 1 by 6 divided by 1 by 3, 1 by 2. So it is 1 by 3. I have written wrongly. If this is the case, this should be 1 by 3. If I include this as equal to, it will be 2 by 3, right. So similarly this is going to be 1 by 3, and this will be 0, agreed. So now we can define the other things, that is total probability, and we had ended the last class with total probability and Bayes theorem. So we can also define now the total probability theorem and the Bayes theorem in terms of random variables. Previously we had defined in terms of events, okay. So that will be like this, that is, let capital X greater than or equal to x be an event B, and again a1, a2, a n be a partition of S as usual. Then we can again say that probability of x given x, that is probability of B, is probability of x given x, x less than or equal to x given a1 into probability of a1 plus dot 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 all the time. This is standard breakage of probability that we have done. So and again we can, this is my conditional probability statement in, if I have this conditional probability, that probability of an event A given x less than or equal to x, I am relating on both sides. Probability of an event A, basically we are talking about probability of an event A given another event B. So I mean sometimes I am putting what is given in terms of the random variable, sometimes I am evaluating the probability given some other event, both you can do. So that is related like this, standard thing, because this is going to be, just simply treat this as an event A given B and then apply the condition probability formula, you will get this. This comes directly, there is no problem. Only problem comes, so these two are very simple to derive. If you just put the probability expressions, then you will get them. Only thing is that here there is a subtle problem, because you cannot define probability of A given x is equal to x in this form, because of the fact that you cannot write it in terms of probabilities, because probability when you have a real line, real variable, for example, then the probability of having x having a particular value is actually 0, when it is infinitesimally small. So therefore you cannot put it in the denominator. See, if you want, if you have this sort of a clause, then it comes in the denominator in the evaluation. So if you put, instead of this clause, you can put in the denominator, because this probability is going to be finite. If you put this, in general you cannot define it like this, right. So in that case what you have to do is that you have to define it in terms of distribution function, rather density functions, because that probability you can and actually this will turn out to be, if you can write it exactly like this. For example, x less than or equal to x2 and greater than x1, what will be the value? You can write, suppose you write that x2 is equal to x plus epsilon, x rather if you take x plus epsilon, and then you take you put this formula. So probability of A x is equal to x can be written as limit of epsilon tending to 0 probability of A given okay. So x is less than or equal to x plus epsilon and it is greater than x. Now if it is greater than x, then x will not be x, actually this should be put in the other way, it should be x minus epsilon, x is greater than epsilon, x minus epsilon, and it is less than x, less than or equal to x. Then you have, what will be this? This will be, by this formula it will be this. So in this case this has come in the second day, so this will be, this is going to be x, and this will be f x1 minus a, so it will be minus f x minus by f x2 minus f x1, right. F x no f x given a minus f x minus given a divided by f x minus f x minus. So this you can write as f x given a dx divided by f x dx. Actually both are small, so I mean something like a hospital rule situation is arising here, but when this dx will get cancelled, you will get a finite value, f x given a divided by f x. That is how this is coming. Both these, as x equal to x, both the probabilities are tending to very close to equal. So it is very, so you will basically get a 0 by 0 form if you want to write it in terms of distributions, but if you write it in terms of densities, then since this dx's will get cancelled, you will get a, that is, this 0 by 0 form will have a definite limit if you write it in terms of densities. In terms of distribution, it may look like 0 by 0, but it will have a limit. It's like the case of sin x by x. As x tends to 0, sin x by both top of sin x goes to 0, x goes to 0, but that does not mean that limit of x tends to 0 sin x by x is not defined. It is defined as 1, right. So because this will go to, both will tend to go to 0, you will have to write it in terms of density functions. Okay. So and then you have the corresponding, finally you have the corresponding Bayes theorem. That is basically what they have done is they have the same thing you are writing, only the denominator is now being expressed in terms of all the posterior probabilities. So, f x given a, so you are writing x given a in terms of a given x, that's the technique, that is what Bayes theorem achieves, that is probability of a given b can be written in terms of probability of b given a, right. So exactly that is being achieved, that is probability of x given a is probability of a given x, it is the right hand side is written fully in terms of a given x. This is nothing but probability of a, this denominator is nothing but probability of a. So f of x given a into probability of a is probability of a given x into f x. Finally, that is the expression. So probability, the denominator is nothing but probability of a. So basically f of x given a into probability of a is probability of a given x equal to x and into f x. So you are writing, you are inverting the two sides. You have to take a little time and think about this and probably solve some problems. I will give you a problem sheet in the next class. So basically what we have done in this class is that we have defined a random variable as a function of the outcomes and then re-derived all the results that we have done in the earlier class. Earlier class we have characterized probability of the events, now we are characterizing probabilities of functions of events. That is what we have done. That is all. Yeah.
Distribution density function we are defining as dfx dx.
Yes.
Derivative of the distribution function.
Derivative of the distribution function.
So if the random variable is a discrete one,
then it will have jumps. For example, our random variable of that coin tossing experiment, what will it have? It will have one impulse here and it will have another impulse here. So the probability density function will have two impulses, everywhere it will be 0, only at these 2 points at 0 and 1 it will have two impulses of size 0.5. That is all. Thank you very much.